In this video, I'm going to talk about 119 angry neighbors problem. So we have this building with 120 units and 119 residents living in it. We call a unit overpopulated if it has 15 or more people living in it. And the thing is, every day, the people living inside an overpopulated unit argue and decide to move to different units within the building. And they do so just because they want to avoid each other. And now the question is asking if this process will eventually stop. And that basically means we basically arrive at a situation where there are no overpopulated units anymore. So let me just give you an example of what the question is asking. Suppose that here we have a unit number, like say unit 10, and assume that there are like 16 people living inside this unit, right? So this unit is overpopulated. And so people inside this unit would start to argue and they just go off to 16 different units. So 16 people live here, 16 people live here. And once, because this is overpopulated, these people would just go off to 16 different units, and no two people would go to the same unit after the move, right? And it's important to know that the question is not actually enforcing these people to go to not overpopulated units. For example, this unit might still be overpopulated when this fellow here is going there, right? So once that happens, it means that the next day this unit is also overpopulated, and so people here would also have to go to other units, and so on and so on. So the question is basically not telling us anything about how this unit is chosen. It's just saying that this fellow here would go off to some other unit, this fellow would go off to some other unit, and so on. So that's the statement. Basically, we want to see if this process will eventually stop. That basically means no matter how these people actually go off to choose their next units after each unit gets overpopulated, we eventually arrive at a situation where there are no overpopulated unit anymore. Okay, so these kind of problems in mathematics in general are basically solved through the idea of potential function. So the idea of potential function. Let me introduce this idea. So, so what's the potential function? Here, the this question is basically if you can formulate it as follows. You can formulate it at a state one, a state of day one, a state of day two, a state of day three. So each state is basically a specific configuration that we have, right? For example, here, let me draw the units here. I have, suppose that these are all the units that I have inside this building, and there are 120 units, and inside each unit there are some people living, some units more, some units less. Note, remember that there are 119 residents, 119 people, and so this is a state one, this is day one, and so after day one some units get overpopulated, and then we make a change, right? So the state would change. We go to a state of day two. So we go to a state of day two, and then after that we go to the state of day three, and so on and so on. And now basically the question is asking if after some point we reach some state, let's say n, where here no units are overpopulated. No units are overpopulated. Sounds good. Okay, now what's the idea of potential function? So we have these states. We have a state S1, a state S2, etc. Suppose that I have a function v. Suppose that I have a function v. Suppose for some function v, which is basically taking an state, so a space of all possible states, and then it would output some positive number. So what exactly this means that, so this function v, for each of these state here, it would output some positive real numbers. And this, and what exactly makes it a potential function is as follows. The potential function of state k plus 1 is less than the potential function of sk minus some constant. So c here is a constant. And if this, so this is like the definition of potential function. And once we have this potential function, we can simply argue that after some state there would be no further states, so it would be an stalemate. So why that's the case, and the main reason is that the potential function takes only positive real numbers, and at each step is reducing by some constant c, where c is a positive value. Let me just also write a constant positive. And so after some step, we would have to stop. That means we cannot go any further. And just to formalize it, we see that v of s n is less than of v of s1. That means state number 1 times c n minus 1. And you can see that this value here, v of s1 is constant. It's just the potential function value at state 1, and this is just decreasing linearly. And because this is always positive, this process cannot go on forever. N is upper bounded. So from here I can see that n has an upper bound. Sounds good? Okay, so for this problem as well, I should try to look for a potential function v and see what this function could be. And let's think about it, right? Let's just say, for example, v of state I is just total number of people inside the building. Can this be a potential function? Can this be a potential function? Can v below be a potential function? And the answer is no, because this v is constant, so it's not decreasing by any constant value. And so this cannot be, answer is definitely not. Definitely not, because it's constant. So what other choices I have? Notice that when we have an overpopulated unit, when we have some unit overpopulated, let's say here I have like 15, 16, or 17 people, overpopulated unit, then I'm going to look at the number of pairs between these people. all the pairs I can draw here, I'm going to look at the number of pairs. I have so many of them, right? And then I'm going to define like v of potential function of state I, sum of, let's say sum of number of pairs inside unit, let's say k. Here I vary k from 1 to 120. So I consider all the units. I look at the people inside the unit, and I try to count how many pairs these people inside each unit would produce, and then I sum all these 120 values, right? And okay, then I'm going to claim that this is a good potential function. Claim v is a potential function. V is a potential function. Okay, why that's the case? Proof. So what would happen, like, suppose that I have a unit like 1 is overpopulated at day k, right? Day number k. And suppose that also like A1, A2, A120 are the number of people living inside these 120 units at day number k, right? And then day number k plus 1, all the people inside unit 1 are dispersed. So I have 0 people living in unit 1. Then for the rest, I may get it. I would have different number of people, right? But I just for like, let's say these people inside A1 would go to units, let's say I1 plus 1 and I A1, I A1. Sorry, here I just write it as unit A1, unit I1 till unit I A1. So they need to find A1 units, right? So if A1 is like 20, they need to find 20 different units and just go there. And for each of these values, I have this is equal to 1 plus 1 A I A1 plus 1. Okay, and now the rest here are the same. So because the rest of the units don't change in terms of the number of people living there, and so the other values for AI are the same. So now what's the change to the potential function? So let me here. Potential function was the sum of pairs, right? Because unit number A is empty, so let me write A plus 1 minus V of sk is equal to, uh, I'm losing basically minus number of pairs inside unit number 1 unit 1, unit 1 at day k, but I'm going to get like new pairs because of these new members inside unit I1 till A1, right? So here I had a unit, here I had a unit, like say it's some people living in it, unit I1, and now this new member is joining, right? And pick this new, how many new pairs this new members is going to make? Exactly a I1. This is the number of new pairs. Number of new pairs, correct? So here I would have, I would have sum of a I, a t, sorry, t from 1, a I t, t from 1 to a1. All right, awesome. Now I need to say that this number is upper bounded by some negative constant. And how we do it? We know that A1 is at least 15. So I have this negative value here, negative number of pairs, is at most minus 15, right? Because this value itself is at least 15. So if you do the negation, you get this value here is at most minus 15. And I need to upper bound this part as well, right? And this part, what's the easiest upper bound we can get for this part? How many residents we had in total? Oops, sorry, I made a mistake here. Let me here. The number of pairs inside unit 1 at day k is lower bounded by 15 uh, choose 2. And that's basically the number of pairs you get with 15 people exactly. The more people you have, the more number of pairs you get. And this value here is basically equal to 15 times 7. And so this is the number of pairs with 15 people. Number of pairs with 15 people. Okay? And for this sum here, the second term here, what's the easiest bound I can use? I can say, okay, we had 119 people and we had like 15 people in unit 1. So this cannot be uh, larger than 119 minus 15, right? So now I'm going to compute this value here. I have minus 15 times 7 plus 120, 119, sorry, minus 15. And this is minus 15 times 8 plus 119. And how do we compute this? So this is 30 times 4 plus 119, and this is minus 1. That's it. That's basically, we showed that this potential function here that we define as the number of pairs inside each unit and then the sum of all of them is actually a potential function. And that completes the proof. So notice that this function here, just as a side note, this is a quadratic function. This is a quadratic function. So let me write it here. Write it here. This is a quadratic function of AI. And more explicitly, this is basically sum of AI times AI minus 1 divided by 2 for I from 1 to 120. And notice that here I first tried a linear function. Here I tried like sum of AI, and it didn't work because this is always a constant. This doesn't change this function, sum of AI. But sum of AI times AI minus 1 divided by 2 does work as we showed here. So this process will eventually stop, and there would be someday that there would be no overpopulated unit.